Chapter 2 is about motion of objects moving in a straight line. It's called one-dimensional motion. That means we'll only be talking about objects moving along the x-axis. Now, can it move along the positive x-axis and the negative? Yes, that's one-dimensional. Positive x, negative x. So we'll only be looking at objects moving along one axis. All right, so the study of motion is actually called kinematics. If you've never seen that word before in your life, that's what it means. Kinematics is the study of motion, but not what causes the motion. You know what causes the motion is applying a force, right? That'll be in the chapters to come. Kinematics is the study of motion. Well, that's a American kestrel flying. It's moving. Nice picture just to wake you up. And the important part there that you have to look at is when it flies in a straight line without any change in direction, its motion is said to be one-dimensional. That is what we're going to do in this chapter. Only one-dimensional, going in a straight line, no change in direction. But when you study motion, you always have to have a reference frame. It is called a reference frame. That means what you are comparing your motion with. All right, I'm moving now, am I not? What is the reference frame? What am I comparing my motion with? Let me make this clear. Let's say that on the freeway there are two cars moving in adjacent tracks with the same speed. And the person in one of them is looking at the person in the other one. The person is mesmerized, has fallen in love, so cannot see anything outside, cannot see the trees, cannot see anything. You know how that is. Oh, tell me, come on. So this person is only seeing the other person, and that's obviously why they want to be with each other, you know. So they're moving with the same speed in the same direction. And if you ask person A, what's the speed of B, what will person A say? Come on. To person A, will B appear to be moving if A is not seeing anything, not seeing the trees, not seeing anything else except the person? Will A say that B is moving? No. Okay? So if B is the reference frame, A is not moving. But as soon as A looks at the trees, what happens? You ask him, are you moving? Oh, yes. And he will say, I think the trees are moving backwards. But are they actually moving backwards? No. So with this, you got an idea of what a reference frame is. You always got to compare motion with something. That is the reference frame. You refer to something. Usually the reference frame is the earth. And my position here, the reference frame is the classroom. The reference frame is the classroom here, isn't it? And if it's a passenger in the airplane, the reference frame is the plane. So you can have different reference frames. At least I hope you got an idea of motion is always relative. You have to compare with something. Take, for instance, wait. Am I moving now? Well, compared to the earth, I'm not moving, but actually we are all moving. Somebody tell me why. There you go. Now you see the difference? So if the classroom is the reference frame, I'm not moving. You're not moving either. But if the moon is the reference frame, oh, we're all moving. Let me see your hands if you understood. Simple concept. Good. Let's go on. Now, we talked about distance and displacement. That's a professor moving to the right, as you can see. Is that positive or negative? Positive. Positive. And delta x, if you can see, can you make out delta x means change in position. Change in x is always x final minus x initial. This is x final. This is x initial. She started from here, didn't she? So this is x initial, this is x final, and the difference between them is plus 2 meters. Why positive 2 meters? Because it's moving along the positive x-axis. Okay? That's why it's positive. Now come to the next example. Before that, what's the displacement of this person? What's the displacement of this person? You didn't see it, but what's the displacement of this person? Come on. Plus 2 meters. Because displacement is a vector. Remember, what's a vector quantity? It also has direction, magnitude and direction. So you got to say plus 2 if it's displacement. Wait, what's the distance? Distance. 2. Distance is a scalar. You don't have to give the direction. You see the distance and displacement difference? You'll see it quite soon. Okay, look at this guy. It's an airplane now. With respect to the passengers, this guy is moving backwards, isn't it? Backwards. So surely his displacement is negative. Because it's along the negative x-axis. Simple things. Again, the formula is the same. It's xf minus x0, but you can see it's minus 4 meters, right? Okay, wait. What's the distance that he moved? 4 meters. What's his displacement? Minus 4. What if he goes back to where he came from? What is his distance? Some of you are saying it. If he goes back to where he started from, the total distance is 8 meters, isn't it? Yes. What's his displacement? 0. Thanks, you got it. This is what we've been doing for 2 days because I don't want to progress. It's like I don't know anything else because I want you to get this. All right, displacement is negative. Take a look at this carefully and in your mind, find out what's the distance in your mind, and I'll give you enough time. The object started from here. How do you know? Because that's x naught, right? Object started from here, went this way. That's why it's minus, right? Minus 3 kilometers. And then returned and stopped here. So that's the initial position. That's the final position. That is negative 3. That's positive 2. There's no confusion there. Easy to understand. In your mind, how many of you know what the distance is? Let me see your hands. If you know what the distance moved is, I'll be so delighted after so much time. Some hands have not gone up. Okay, shout the answer out, please. What's the distance? 5. Thank you for giving the unit. Without unit, it doesn't make sense. It's 5, right? Good. Distance is 5 kilometers. What's the displacement? Don't say it. Think. What's the displacement of this object? Think about it. Who knows the answer? And you're sure about it. Wow, you're sure? That's good. That's a good sight to see so many people being sure. Let's go. Thank you. Negative 1. I like that. Did you understand why it's negative? Because it ended up on the negative side. You see that? That's why it's negative 1. So the distance is 5 kilometers, and the displacement is negative 1. Well, delta x is xf minus x naught. That's 2 minus 3. That's how you get it, right? 2 plus 2 minus 3. Difference, distance is a scalar, displacement is a vector for the 100th time. Trying to give you this idea. And on the right side, you see that if it's going to the east, it's positive. To the west is negative. North, somebody, positive, because that's the positive y-axis. And south would be negative. Yeah, that's the rule we're going to use. We're going to follow. Got it? It's easy enough. It's crazy easy. What's the difference between a vector and a scalar? Again, vector has both magnitude and direction. Scalar has only magnitude. Can you give me another example for a scalar quantity, somebody? Or the only thing that you know is distance? Or maybe speed. Okay, we talked about speed. Temperature is a scalar. Come on. Height. Height. Weight. Okay. Weight is actually a vector. Weight is the force of gravity on you. Force is a vector. Height, well, you always measure height upwards, so.
What were you asking? I thought you were asking for a question.
No, I was asking for a scalar. Yeah. Give me some more examples. What about time? Yeah. Hey, what's the time? And have you heard anybody say it's 10:30 to the west? It's 10:30. What about mass? Mass, what's the unit of mass? What's the unit of mass? Kilograms. If somebody asked me what's the mass of this iPad, would I say 2 kilograms to the north? Doesn't make sense. So mass is a scalar, right? Okay. I gave you so many examples. Time. I wish we could stop time. I would have stopped it when I was 16. Time always changes. So it's always going to be delta t. What does that little triangle show? It shows that it's changing. That means change in time. And change in anything is final takeaway initial. And change in time is Tf minus T naught. And usually we take T naught as 0. Therefore, instead of writing delta T all the time, I might just write T, okay? But you understand, whenever I write T, that means I'm talking about the change in time. And we always measured from 0. That's what it means. Simple thing. Very simple. No stories today. Average velocity and average speed. Now, average velocity is displacement divided by time. And this is how it's written. If you have a line over this, I'm sure many of you know this, right? That means it is the average. It's the mean. So delta x by delta t. That is xf minus x0 by tf minus t naught. Isn't that what we've been saying so far? Therefore, average velocity is delta x by t, a very important equation which you should write. Delta x is in meters, time is in seconds, therefore the average velocity will always be in meter per second, isn't it? But the thing is, how many of you got a ticket in your life at least one time, a ticket for speeding? Ha, goodness. Okay, thank you for being honest. Was the police actually giving you a ticket for the average velocity? Or was it for the velocity at that particular instant? At that particular instant, right? Therefore, it's called instantaneous velocity or instantaneous velocity. How do you define that? Means that's that at that instant. So what's the time factor there? If you're talking about a particular instant and that instant is so small, can I say that the time is almost 0? Can I say that? At that instant. It's not even 1 second gap. It's just that instant. So when you define instantaneous velocity, you're talking about the velocity at a particular time. And that is why you got all those tickets. Thank you, by the way, for getting all those tickets. You supported me. You supported the country because the country needs money. But it's not good to overspeed because speed kills. Okay, be careful. And after you have gone through like 10 chapters of physics, all talking about motion, and many times I'm going to bring an example of a car here, you will not speed. I promise you. You will not look at your cell phone when you're driving. Because if you're doing that, I'm going to prove scientifically that it's a very dangerous condition. We'll prove it right now today. Okay, let's go on. That's fine. Running. Is this going along the positive x or negative x? Negative x. I just wanted to throw some pictures so you wake up. And we already talked about this. East is positive, west is negative, north is positive, south is negative again. Okay. Speed. How is speed defined? Speed. We've been stuck on speed and velocity for like 2 years now. Come on. Speed is distance divided by time. What's the unit of speed? No. Meters per second. The unit of distance is meter, and the unit of time is seconds, isn't it? So it's meter per second. That means their units are the same. Speed and velocity, the units are the same. The only difference is that speed is a scalar. Velocity is a vector. Okay, so you divide scalar by a scalar, you get a scalar. Velocity is displacement over time. Displacement is vector. Time is scalar. Velocity is vector. Don't be confused. Just trying to show each one there. Are you all clear with all this? All right, snail. Haven't you heard that? Moving at snail's pace. Have you seen them move? Have you seen snails move? Actually, sometimes I see one outside my window on the glass. Man, it's just goes so slowly. That's exactly how some students walk when they are in college. Anyway, let me stop it at that. Some person goes from the home to the store 3 kilometers and returns. What's the displacement? You already see. There's nothing there. Now, the graphs, we're going to take some time on this. For some students to understand a graph is tough. First of all, a graph has an x-axis and a y-axis, right? What quantity do you take on the x-axis always? From high school, do you remember independent variables and dependent? I'm sure they spent a lot of time there, you know. No? What is an independent variable? Let's say I'm trying to track my position against time. Okay? So I start from here. So I measure my position from here. That's the origin. Oh, this is the x-axis. You have the y, and you have the z-axis. Do you see that? But today we're only talking about the motion along the x. So I start from 0. I have a stopwatch, and I time myself. And I stop, and I look at the time. And I look at the distance. Now, which one of these quantities am I able to change if it's another person walking and I have the stopwatch? Let's change the example a little bit so you're not confused. I have the stopwatch. I'm tracking the motion of another person. Which is the quantity that I'm able to change? Another person is walking and I'm tracking his time. I have the stopwatch. Which is the quantity I'm able to change? That's why it's called an independent variable. You can take his distance after 1 second, each second, or you can take his distance after 2 seconds, right? That's you who decide. And the independent variable is always taken on the x-axis. That's the important thing. The independent variable is always taken on the x-axis. And what's the independent variable here? Time and position. Which is the independent variable? Time. So you will take time on the x-axis. And what do you take on the y-axis? Position. All right, take a look at this first graph that's coming up. Take a close look at this one. Can you make out the numbers? I think you can, right? Time here, 0.1, 0.2, 0.3, 0.4. This is position. They've actually taken it in kilometers. I don't like that, but anyway, it's in kilometers. Can somebody describe this motion to me? Take a look at it. Think about it. What is the object doing? I'm going to pause. Okay. Did it go back to where it came from?
Yes. Zero displacement.
Is the displacement 0? Yes. Is the distance 0?
No.
What's the total distance?
6 kilometers.
12 kilometers, isn't it? It went up 6 and came back 6. Come on, man. Right? All right, what's the average speed of this object? Calculate, go. Calculate the average speed of this object right now. What do you mean by average speed? Distance divided by time, isn't it?
Yeah.
Yeah. What's the total distance? 12. Yeah, just keep it in kilometers, but give me the proper units now. Divide by, what was the time taken? 0.5. What's 12 divided by 0.5? 24. And the unit?
Kilometers per hour. Meters per second. Meters
No. In this case, the unit is
kilometers per second.
per second, yeah. Kilometers per second. Isn't it?
Oh, yeah, per hour.
Where?
Right there, it says 10 hours.
Oh, the time is, I didn't even see that.
It's so tiny.
I didn't even see that. You are right and I'm wrong, but not always. No, yeah. So the answer is 20. I apologize. It's on YouTube. So it's 24
Kilometers
per hour because I didn't notice. But you're good. I wanted to teach you something. You got it. Now go to the next graph. What's the difference between the first one and the second one? I'm going to test you. There's one question based on a graph on the exam. Look at the next one. What's the difference? What's on the x-axis? On the x-axis. This time I've seen it. It's dollars. What do you have here? Is velocity a vector? Yes. That's why you have both a positive side and a negative side. Did you see that? Because it's a vector. Oh, is this the graph of that object? I think so. I think so. Look at it. Look at it. What's the velocity? That's 10, that's 15. So what's the velocity?
10.
No, that's not 10.
Oh, it's in between.
It's 12. Oh, you know how we got the 12? Look, 6 divided by half of this time. How much is this? Isn't this 6? Ah, isn't that 6? Okay, so that's like 12 kilometers per hour. Hey, what's happening here?
Stalled.
That's because at this point there was a sudden change in direction. Did you notice that? In no time. It's like somebody started walking from here and didn't even stop and went back. You see that? In no time. So that's why that part of the graph, it should not go this way because that would mean time changed, isn't it? It's going straight down, no change in time. But since the object is going backwards, it has to be negative 12. How many understood? Let me see your hands. First, because velocity is a vector. The object is moving that way, isn't it? So that's positive. And within no time, it changed direction. So went down. All right, the next one, the last graph. Take a look at it. What's on the x-axis again? Time. And what's on the y-axis now? Speed is? Okay, it has nothing to do with? That's why it doesn't have a negative axis at all. Do you see that? And didn't we calculate, what's the speed now? 12. Consistent. Do you see the spot? What is that? That's the point where it turned. Just so you see. You don't have to, that's the point. But it keeps going in the positive direction because speed is a scalar, right? Okay, when we do problems, you'll understand more of it, okay? Let's go on. Otherwise, we'll never finish. That's where I was explaining all this. You don't need all that. I must say the toughest concept for a student to understand is about acceleration. People think they know what it means, but they really don't. Acceleration is the change in velocity in 1 second. That's what it is. Acceleration is change in velocity divided by time, or it is called the rate of change. Many students do not know the meaning of rate. When you hear that, that means it's per second. Okay? Rate of change means how much it changed in 1 second. All right, that was too fast. So that's, somebody read this for me. What's that? Average acceleration is equal to change in velocity divided by change in time. And surely change in velocity is final velocity take away initial velocity divided by the time, right? Okay, change in velocity divided by the time. And like I said, I don't like to put this always as TF minus T naught, so I'll always put T, okay? That's all. T, because time always changes. The unit. What's the unit of this? What's the unit of this? Meter per second. What's the unit of time? Second. So if you divide, what happens? Now, some people think that it'll cancel out. No, please, no. No. It becomes meter per second squared. That's the unit of acceleration. That's why you get it like that. Okay, let me give you an example, and you try to find out. Let's say that You start in the morning when you were driving. What was your initial velocity? Okay. And let's say you are a perfect driver. Nobody like that here, but just imagine. Which means you will step on the gas just exactly the same way. You won't go, ooh, no, you just. So that means you're going to have an acceleration of, imagine, 1 meter per second squared. Are you writing? Are you focusing on writing or focusing on understanding? I don't know. But if you're focusing on writing, you are doing something wrong. Focus on what I'm saying. Write less, okay? Do both, but try to get what I'm saying. Acceleration is 1 meter per second squared. Who can tell me what is the velocity of this car after 1 second? Just put your hand up, don't shout it. What is the velocity of this car after 1 second? If you have your answer, put your hand up. See, this is exactly what I said. People don't understand the meaning of acceleration. What do you mean by 1 meter per second squared? That means the velocity changed by 1 meter per second every second. Are you with me? I can only say it again. Same way. Velocity increased, in this case it's increasing, by 1 meter per second every second. And I'm asking you, what's its velocity after 1 second?
1 meter per second.
Okay, what's its velocity after 2 seconds? What's its velocity after 10 seconds? You got an equation. You got it. How did you find it? This is what you did. Oh, the acceleration, you multiplied it with the time. Isn't that what you did? The acceleration is 1, and I said 10 seconds, didn't I? So you said 1 times 10, 10. Okay. No, but let me change this question a little bit for those of you who are really listening. Let's say that I didn't see you when you started out. I saw you when you were already moving at 10 meters per second, okay? It's like I'm tracking you. And so I see you when you're moving at 10 meters per second. So as far as I'm concerned, your initial velocity is 10 meters per second. Because that's what I saw you moving at. And now the question. What's the velocity that you would have, according to me, after 10 seconds? Don't say it. The initial is 10. You're having the same acceleration. 1 meter per second squared, okay? What's your velocity after 10 seconds for me? How many know the answer? Hand up again. We have the exercise of putting the hands up here. That's 3 hands, and the others are gone. 4. Come on. The initial is 10. And from there on, it changes at 1 meter per second every second. So how much did it change after 10 seconds? Wait, how much did it change after 10 seconds? 10 meters per second, A times t. But to get your final velocity, don't you have to add the initial? Wouldn't I feel that your velocity is 20 meters per second? Correct? Because you already had what? You already had 10 meters per second. And you changed by that much. Usually I don't put the units, but I just wanted you to see. Look how the units work out. Seconds, square, gone. So you have 10 meters per second plus 1 meter per second, isn't it? Plus 10 meters per second, I mean, which is 20. It's like,